you. So I guess the first thing I want to say about this talk is that it's not going to mention the term underwater knife fight at all. I've never had that used at a functional programming talk before. I thought that was pretty cool. This is on pure data. I don't really know why it's called pure data. It seemed appropriate. It was probably just sounded a bit better than lazy data, which might be the other one you might choose. It's all about a bit of a thought experiment I've had, some ideas I've been developing that I named Datum. It's a few things. It's a data representation, it's a data model, and it's a bunch of operators. You know, pretty simple stuff. The reason I'm thinking about this is because I'm pretty not happy with the choices I've got at the moment in the technology in these areas, both the in particular data models and operators. So let's start with a motivating example. We've just got a bunch of JSON data here. It's a couple of share prices for two companies. Now there's a bunch of things in there. There's a little bit of hierarchy, a little bit of nesting, you know, a few different aspects, and we're going to kind of look at how this data might be modeled in different using different techniques today. Now, what we're going to want to do to this data is we're going to want to create some aggregates. So you can see over here we've added a return, which is the percentage return that the company gave to its shareholders by its share price going up and down on the since the previous day, and that's obviously derived from the share price of the security. So we've got Google and Tesla. It seems to be the two go-to companies that you have to use in a demo these days. And we've got, for a few days here, some closing prices, and we've derived these returns. Now we're also going to calculate an average price, which is an aggregate of these closing prices and is obviously one level higher up in the hierarchy. So what we're trying to do here is really build a simple, easy to use and consistent analytics query engine. That's all it comes down to. Now those little examples I provided there are just little tiny snippets of the sorts of things you do in analytics. Let's have a look at the relational the model. You know, face it, everyone loves the relational model. It's the best one in the world, I reckon. Not really. Okay, so you've got two tables, and there's a one-to-many relationship between them, and if you want to, you can create a materialized view or actually create some extra columns in there to store this data that you're wanting to derive in with the raw data. Now, if you want to get really fancy and split things out, you might, you know, create a day table as well if you want to store additional information at the day level. You've got the flat model, which is, I don't know, using grep, using Hadoop, anything that'll basically read data as if it's just a bunch of bytes. You've got arrays if you want to take a NumPy or similar approach. That's the same data stored in a two-dimensional array. When you're dealing with arrays, often you need to be thinking, what do the different dimensions and or rows and columns, what do they relate to? Now in this array, we have to remember that the companies is the x-axis and the days is the y. Here's an example just using with NumPy in Python. We've got a two-dimensional array there built in NumPy, which is the data on the previous one, and then we construct some new arrays which represent the previous price and the current price, and then we subtract one from the other, and then we can extract a return series. It's all a little bit confusing because we're having to map all the time between an array and what it actually means in the real domain that we're dealing with. The next step up is to bring a whole bunch of different arrays together. So here we've really got three arrays. Three series. We've got a date series, we've got a company series, and then we've got a two-dimensional array which represents the prices, and that is essentially called a data frame. So I don't know if many of you have used the pandas library. It's quite popular. That's another Python package. But it effectively bakes in this design where you have a bunch of different arrays representing labels and representing data, and it presents it in a nice, friendly way. Here's an example of using pandas. So this is loading that same data into a pandas data frame. Pandas distinguishes between the index and particular columns, but you can see that there is a recognition here of a kind of hierarchy, a kind of nesting, in that all these days are nested underneath Google, and these days are nested underneath Tesla. Now, under the covers, the implementation of this is not all that crash hot. I think it's actually a little bit inefficient, but I think the representation is at least useful. Now, we can do things like, say, price.mean at level 0 and collapse a little bit of the dimensionality and create some aggregates. That's quite easy, and it's really nice how it converts it into a form that we can look at and understand. Similarly, we can say with our company data frame, we can add some data into there, which is the average of all the closing prices for those particular companies, using price.mean level equals 0, and then we can see here what the data frame has changed. Similarly, we can go and grab the return series that we created before and inject that into the data frame, so we can see the raw data and the calculated data alongside. That works really well. And we can also do this pretty cool thing called unstack, which takes a nested value here, or a nested dimension, and then actually spreads it across the other axes. Now, this is handy when you're doing calculations on how much a value has changed, because of course if you do it over the entire data set, you'll get these edge cases where it's transitioning from one stock to the next, and you'll have some sort of a crazy figure. Whereas putting it into this style of data frame allows each stock, each company to be calculated separately, so they don't contaminate one another. So that's a calculation there. We're saying the return is the closing price minus the previous price divided by the previous price, and then that's the data frame we get out. We can then do a restack, which is basically the reverse operation. It takes the data frame that has the dates along the x-axis and then brings them under a nested value with the row index. And then collapsing the whole thing together, we can bring in the derived data and put it right alongside the raw one. Now you can see here that if we just basically said the return is the change since the previous value, we would have had an error value here, because it would have been converting between the latest value for Google and the first value of Tesla. So there's an element of dimensionality in there that's kind of helping you solve the problem that you're trying to sort out. Okay, so if we look at all the major data models that we use today and look at what the features of them are, I mean, this is all really approximate, not saying any of this is absolute, but CSV files are kind of simple. The business guys can send them to you and receive them. They're a little bit hacky, which is kind of a good and a bad thing, and we can process them in a streaming fashion. So it can be a massive CSV file, and we don't have to read the whole thing into memory. We've got nested data in the form of JSON. It's good for grouping things. We've got data frames that we just looked at. I think the particular strength of data frames is the labeling aspect of it. So we can draw the context together of two different arrays and see what they're actually representing. And we've got arrays, which are great for doing lots of numerical work, so very fast aggregations and whatnot. Okay, so two that I've left out: object-oriented and relational. I hope nobody is getting offended at that, but I just kind of feel like they're too complicated, too much overhead. So what I've tried to do is say, okay, well, none of these models really do everything that I want to do. Is there a kernel in there that is not as complicated as relational or object-oriented? that's going to allow me to do the things that I want to do, and I'm not going to be forced to be jumping between these different modes. So I'm not going to have to reach for the right tool for the right job, because maybe there's a more general solution to this. A lot of people will be asking about OLAP, if you've have experience with them at the moment. That's a fantastic question. It's a really detailed one. I guess I just wanted to mention it to say that I'm not going to be mentioning it other than that. OLAP's a huge space. You can certainly build OLAP style things in Datum, but they're certainly not equivalent. You know, OLAP is even more complicated than the other ones we've avoided. So what is the Datum model? So the Datum model comes down to three really, really simple things. When we talk about Datum, try not to think about an SQL database. Try to think more like a file system, something that's really, you know, quite low level. So what is it? Contain your enthusiasm, reduce your expectations of it. So we have a dimension, we have a column, and we have a size. So a dimension has a size. That size can be of three different types, which we'll get to in a second. But a dimension can contain many children, so it's a tree graph, and a dimension can contain many columns, and that's basically it. There's really nothing more to the model than that. So if we look at it in terms of Haskell code, this is the only Haskell code you'll have to look at. We'll start with the simplest one, size. There's three different constructors of size. There is one, which represents a dimension to which there is only one single value, so it'd be like unit. Really the only reason you'd use size 1 is for the root dimension, which you only ever have one instance of. There's a fixed size, which means that every child value in a particular dimension is always of the fixed size. So if I explain that a bit more, say you've got information on cars, and you've got information on different parts of a car. So you've got models of cars, and then you've got you know, a sub-classifier like, you know, steering system, you know, engine, etc., etc. If those sub-items are always of the same size, then you use a fix. You say there is 5 of them, or whatever. If you want to construct a regularly shaped array, so you've got a 10 by 20 array, that would just be 2 dimensions with a dimension of 10, and then a child dimension with the other axes. And then we have a var size, which is a variable size, which is to say this is a ragged or a jagged array, meaning that each child in a particular dimension has a different size to it altogether. So an example of that might be if you've got a table with a string in it, and the string is always of varying length. You would actually describe the length of the string by saying that the size is a list of integers. Okay, so the most complicated one is the definition of dimension. It has a name, it has a size, which we talked about before, and it has a set of children and columns, which are basically just in a map, and they're referred to by name. And you have a column, which is pretty darn simple. You can see that there's a free type variable there. Yeah, just ignore that. In the prototype that I'm implementing at the moment, we actually use dynamic types to kind of keep the traffic moving, so to speak. But basically, a column is just an array or list of values. Okay, so here is an example, or the example that we looked at initially of that JSON data. We're going to start to look at what would that look like if you were to tease it out under the Datum model. So we always start with a root dimension with one instance that's given. You never have more than one. And then under that, we have a company dimension, of which we have a size of fixed 2. So that is to say that there is 2 companies for every root instance. And because there is only ever one root instance, that means we have 2 companies. Now those 2 companies are Google and Tesla, which came from the JSON data. And one piece of data that we want to store on a per company basis is the code. So that's the stock code GOOG TSLA. Now the way that would be stored in Datum would be to say, okay, this is a variable dimension, and of these two companies, the first one is of length 4 and the second one is of length 4. And then we store the columns. So the colouring here is the green is dimensions, sizes, and then the white is the columns. Now you then store all the data in dense form, no delimiters or anything like that, and then that gets processed in conjunction with the dimension size to actually give it meaning. Now that meaning is going to vary depending on which level of dimensionality you're actually looking at. If you're just looking at individual codes and you don't really care about any data up here, you could just look at that in isolation and say, okay, well, I've got two items. The first one is Goog and the next one is Tuzla, and that's it. But if we want to then look up at a higher dimension, we can possibly get more information on that. Now, another bit of information that's in the JSON is the name, and similar thing. This is a variable sized dimension. The first size is 18 because that's the number of characters in Google Inc. Class C, and then 16, which is the length of the string Tesla Motors Inc. Now, the next bit of data that we've got is this extra subtable up in the JSON. So, because we have another level of nesting, we have a 0 to n relationship going on here. We create another dimension and we say, okay, this is the price dimension, and the size of that dimension is 4, 4, because we have 4 rows for each of the companies, as it turns out. Every column, because remember before, a column lives within a particular dimension. These columns will have the same shape to them, but they will have different data, and we basically store it in dense form. And yeah, I've just put a few of the items there. Now, using the example we had before, where we calculated a couple of aggregations, we would be able to add things into this schema to say we want to calculate a return, which the shape of that return data would actually fit under this subdimension, but the average price data would have a different shape. It would actually sit up at the company level, and that is all derived for you. So depending on what type of a calculation you make. Okay, so the fundamentals I mentioned before. The root dimension always has size 1, and everything always starts from the root dimension. I hadn't mentioned this. The columns they're always fixed width. So you can't have a string column. That actually doesn't exist. You have a character column, and that character column can be in a subdimension, meaning you can have a variable number of them. So that's the way you actually store a string. So there is no notion of a column containing a stock code that can be of different width. You can put tuples in. That's fine, but you can't put lists of things in there. Anything variable width needs a dimension. So something's I don't know, say you have a case where in some cases you want to store 16 bits, another one you want to store 32 for whatever reason. No, it's all got to be completely fixed. So we're really kind of dialing down the complexity of this and making it simple. Arrays are modelled with nested dimensions. So if you have 3 or 4 levels of nesting, that just basically means you've got a 3 or 4 dimensional cube. And you can have different combinations of regular and ragged axes in there. Optionality, so nulls, maybe, etc. There's no support for it at all. That's just another case of a dimension which has 0 or 1 instances in it. And I mentioned before, strings are just subdimensions with characters. Okay, so looking at how we manipulate that schema, that model in Haskell. I'm a Haskell newbie, and a couple of things I've learnt that I thought might be helpful to people. So look around. There's a couple of pretty strong kind of Haskell brains in the room, so I ask for their patience. The state monad, I've used quite a bit with this. The state monad, from a layman's perspective, manages what feels like a global state that exists for a particular type. And instead of having to pass it in and out, you're able to not have to explicitly drag it along with you all the time. It feels to me like it's kind of you're able to mutate something in a pure environment, but that mutation is at least contained to your particular type. Zippers is another one. I don't know if anyone knows the zip function. That has absolutely nothing to do with it whatsoever. That was a confusion I'd kind of made for the first 5 seconds when I had a look at it. It's a functional way of allowing you to edit a graph, would be the way that I would describe it. And there's actually a lot of really great theory behind zippers and some really great papers which I've read. Apparently, you can derive a zipper for any abstract data type that you want. Here's, I think, pretty much the simplest zipper that you can imagine. So a big feature of pure programming languages is that data is immutable and you can't change it. So if you're wanting to edit something, if you're wanting to change a list or a graph or something like that, that presents a lot of problems because you effectively need to rebuild the data structure every time you make one change. Now, a zipper in the case of a list is this type here, and basically it is a type that contains 2 lists and an item in between. Now, this item in between is kind of known as the target or the whole of the zipper, and it's kind of like you're going around with a magnifying glass and you're focusing on one particular type, one particular item. Now, as you move to the left and right, you're creating new lists and a new zipper that focuses on the next item. So you're just creating more and more of these immutable data structures, but it gives you the feeling, it gives you the illusion that you're actually moving around the data structure, and that allows you to make changes to things. So you're able to change with a list zipper the item that's in the whole. Whereas anyone that's used Haskell will know that you can't just change an arbitrary item in a list. You basically need to regenerate it. Now, that's the simplest case of zipper. I don't know if the term zipper really, I don't know. I don't know if it's necessarily a good one. I mean, zip I think is a well-named function, but zippers for these complex graphs, I'm not sure it makes all that much sense. This is the zipper for Datum. You can see why I didn't get any graphic design kind of qualifications. Looks pretty terrible. Maybe stick with the code. It's less poisonous. I've called it lock for location to say, okay, this is a location in the Datum schema. It's got parent, siblings, a target dimension, and a target column. So the whole, the thing we're focusing on, the thing we've got the magnifying glass over, I'm referring to as the target here, the target dimension. Now remember, dimensions can contain subdimensions and subdimensions, etc., etc. They can have columns, multiple columns. But this zipper overlays siblings and parents as well. So while I'm focused on this particular dimension, the parent of this dimension has other children, which are the siblings, which are modelled along here as in another map. And then as I change my focus from one dimension to another, I'm essentially removing a dimension from the siblings and putting my current focus in there. And I'm doing that in a pure way. So I'm modifying the state of the zipper as I move around. I could write a function for this to say go up, which means go up to start focusing on the parent, which would effectively take the target that I'm looking at and all the siblings and put that under as a child of my next parent in my hierarchy. So the parents here is essentially a list going up to the root of my actual ancestor dimension, but also the siblings of those ancestors. So I don't know if you can kind of picture all that in your head, that as we move around this graph, we are keeping a distinct line of the hierarchy between a particular dimension and the root, and all the aunties and uncles and other relatives are being kept in a map. But as we move up and down and around, we're basically reconstructing the schema as we move. Okay, so looking at the type of operations that you can do in Datum, there's a couple of different kind of categories of them. The first one is the shape agnostic stuff, so map. You know, if you've got some data, okay, I've got a stock and I've got, you know, share prices over a bunch of days, and I apply a map to those prices. Obviously, that answer is going to have the same shape that the original data had. You're going to have other operations like, you know, I don't know, arithmetic, any kind of function that doesn't have any level of dimensionality in it will be completely agnostic to it. You've got shape reducing operators. So a fold is a good example there. So that may be, or in this case, a segmented fold. So if we're doing a fold for each item down here, maybe we're aggregating those items together. What will happen is that when we aggregate them, we get a result in the next level of dimensionality up, and so we've reduced the amount of dimensions that we've got in the model. And then we've got shape creating operations like group. So we might have some data, and we're going to do a group by that's effectively going to create another dimension sitting in between. So you can see in a lot of these cases, the original data kind of stays as is and is still useful just as it was before, but we're able to overlay onto it something entirely new, like a new level of dimensionality. There's the last category I've got here is shape transforming. So this is stack, unstack, and swap. So stack and unstack are quite kind of complex beasts. I'll talk about swap now. Swap is basically a transpose. So it's changing the order of dimensions. So instead of year, city, I want to have city, year. It's going to transpose the underlying array and switch the dimensions around. The last one is sorting, which is kind of like the heavy lifting operator. This is where I got into the whole zipper thing, in that sorting is a hard operation in that you want to sort by something, but you need to take all the things that you want to reorder with you. So you're wanting to sort a whole lot of things. You're not just wanting to sort one small set of data. And the use of the zipper is great because you end up being able to create these kind of temporary views of your schema that you end up throwing away. Maybe you use it to define a region of things that you want to sort, and then you reintegrate the things that you want to keep into your original schema, and then that's it. So looking at the philosophy behind Datum, it's all about a commit log, append only. You can't actually change any data that you've posted to it before. We always preserve the original entropy that data came from, so it's in the original in the original source form. We don't transform and then throw the original away. And we often transform it into lots of other forms. So you might have two versions of a data structure. We'll just transform them into both, and then when an older version gets deprecated, then you can stop generating it. So you could think of it as I don't know, an SQL database where all you can do is write to the log file, and you never truncate the log. You never do that at all. And every table in the SQL database is effectively a view of what is in the log file. So in theory, you can regenerate the whole data store from the original log. So the characteristics of it is that, well, the downside of it is that you have long commit times. This is a data store where you don't have tiny little transactions being committed all the time. It's designed for long commits, and therefore it's compatible with the Lambda architecture. I don't know how many people are aware of that. That's where you split your data architecture into the speed layer, which does all the real-time stuff, and then you've got the heavy lifting, the kind of big data work being done in the background, and they basically work together to provide the illusion that they are the one data store. And data frames are good. They're good they're good abstractions for people to get their head around. So data frames can have a whole bunch more than they've got currently. Like the amount of dimensionality in a data frame, I think, is quite minimal. There is the opportunity to be able to provide arbitrarily deep dimensions with data frames. In fact, have n-dimensional data frames. You could have data frames where each cell has data frames. I mean, it just doesn't stop. Whereas the current data frames people are using in things like R and Python, they're generally two-dimensional. You can go to, certainly in pandas, you can go higher, but you just find that the support kind of drops away. Now, modeling that data frame that we just saw in Datum would look like this. And then the three components that I was talking about before, you've got the data, and then you've got the labeling on the x-axis and the y-axis, are basically these three dimensions here. And if you were to swap them around, you would be able to reshape the data frame. The idea being is that you can model a data frame in Datum, but you don't have to do everything with data frames. Data frames are just a useful abstraction, if they assist you. The whole point behind all this, from a commercial perspective, is to actually build a data store in the cloud, an analytics engine in the cloud, and that is to create a data store where people actually upload their data and then rent access to analytics on the data to third parties. So you kind of think of it as like an app store for data. But for the time being, it's a functional programming thought experiment / bit of fun. Thank you very much. You've been a wonderful crowd. Any questions or yes?
So you said you keep the data as is and you just append a bunch of transactions, right?
Yep.
Fully append only. And at the same time, you also said it was commits were long. So
yep.
Let's say I wanted change my data set and kind of do a group by companies, group by sector. I'm adding a layer. Isn't it just a matter of appending a transaction saying I've done a group by?
Well,
why is it slow?
Yeah, okay, so it's slow only when you've committed new data to it.
I see. So it's changed the underlying, but not the structure.
No. Structure you can add and remove dimensions and reshape things without affecting anything. It's just in the case that you're wanting to commit new entropy, because the entropy might impact a sort, which is just going to change the whole thing. So the idea is that it's an analytics store, so you kind of do hourly, daily ingestion, whatever. And then you have things pre-computed to provide kind of fast answers down the track. It's not designed to be a real-time store. If we want to do the more real-time stuff, then that would be like an in-memory thing sitting in front of it.
So the point about the commit, the append-only log.
Yep.
Is very, very familiar from the stuff I talked about, which is the left folder over events.
Yes.
So, I mean, I probably...
You could see the whole data store as being a left folder over events. Yeah.
Okay.
Yep. If you see the whole data store as being the state that you're carrying.
Is the dimensionality the state? As you add new stuff, the dimensionality changes, or is it the...
No, dimensionality never changes when you add new data. Dimensionality is always a result of the transformation that you're applying to that data. So it's always kind of typed in that respect.
That's projection.
Yes.
Of the stuff that you just added.
I've not had it's not a case where you can throw data at it and it'll kind of dynamically create dimensions. You can dynamically create instances in those dimensions, but not the dimensions themselves.
And to save structure, do you basically serialize that tree of, I forgot what it was called, dimensions? Is that basically how you keep track of your structure?
Yeah, that's right. Yeah. At the moment, it's it's Haskell types. So it's like a DSL of sorts to describe it. Yep.
What happens if at some point there was a data that was wrong and you need to actually alter one of those data?
Yeah. So someone comes and says, I uploaded a really embarrassing photo and I really, really want it to be deleted. Yes, so that's kind of out of band in that you'd have to take down the data store, single user mode, edit the log, mutate it, and then bring it back up again. In practice, what you'd do is you'd say, I want to run a transformation of the log, which is everything except the thing that I want, and then I'm going to swap the log to be that new thing, which is, kind of mutatey, but that's what you'd have to do. Yeah. Maybe Ashley Madison could kind of work out the delete key, possibly, especially when they sell me that product to delete my data. Oh. Trouble they cause.